Go ahead when you're ready, Bob.
Okay, I think we may as well get started. There probably will be a few more people come along. We've been trying, Barbara Mann and various people, and I have been trying to arrange for Dr. Werner to come and speak with us. And I'll just say a few words about him. He got his PhD in astronomy from Cornell, and he's been with JPL and Caltech and the Spitzer Space Telescope for a long time. If I'm not mistaken, and I'm sure Dr. Werner will correct me if I am, I believe the original plan was that the Spitzer Space Telescope would only have a lifetime of 3 or 4 years, but it did very well and exceeded what people expected. And so, as you can see in this slide, its lifetime was 17 years. And we don't know how long the James Webb Telescope will last, but the longer the better. And Dr. Werner was principal scientist for the Spitzer Space Telescope. And as I said, this accomplished more than was expected, and that's why its lifetime was extended. So at that point, I think I'll just turn the microphone over to Dr. Werner.
Confusion. So I'll be talking about astronomy as we do it in the infrared part of the spectrum. 2 missions here. I'll be describing the Spitzer Space Telescope, which I worked on myself for almost 40 years, almost 50 years. And the James Webb Space Telescope, which was recently launched, is returning great science and building on the successes of Spitzer and the Hubble Space Telescope. Now, by way of introduction, what we see here is the cover of a book that NASA published in 1986 called The Great Observatories. And the Great Observatories program envisioned the simultaneous or successive operation in space of powerful observatories across the electromagnetic spectrum, starting the electromagnetic spectrum going from high energies, gamma rays, which are seen by Fermi, to infrared, which is seen by Spitzer. The only part of this spectrum can be seen from the ground is what's called visible light, which is a very small piece of it right there in the middle. But we now know that we use observations across the electromagnetic spectrum to study astrophysical phenomena. The scale underneath the spectrum is a temperature scale, and it shows that for temperatures between about 100 and 1,000 degrees, things radiate primarily in the infrared. You'll be familiar with this with a heat lamp, or when you go to your doctor and they take your temperature with a thing that looks a little like a pistol. They're actually measuring the infrared radiation from your forehead, which tells them the temperature of your forehead and whether you have a fever or not. So this infrared stuff are things that we're all using every day nowadays. Now you might ask, why do we need all these different telescopes? And that is shown here with my picture of my trusty dog, Rusty. Rusty is seen in the infrared in the big image at the top, and at visible light in the lower image at the right. In visible light, what Rusty is doing is radiating, reflecting lamplight or room light. In the infrared, what Rusty is doing is radiating his own heat. So if we came back at night and took these pictures, Rusty would disappear in visible light, but still be there in the infrared because his temperature wouldn't have changed very much. And when we look at Rusty's image in the infrared, we can see that he's hottest, there's a temperature scale over here, where you're looking closest to his blood supply, like his mouth and his eyes, and coldest, where his fur is thickest and provides the most insulation. And since Rusty's a proper dog, he has a cold nose. So you can see, first of all, that even relatively simple things like dogs look different in different parts of the spectrum. You also see how you can use the properties of the infrared emission to diagnose the physical environment or the physical system that you're studying. Now, the subtitle of this talk is The Cold, the Old, and the Dirty, or The Old, the Cold, and the Dirty. And let me explain this with a few examples. In the infrared, because of the expansion of the universe, when we look back in space and time and more distant objects, their light shifts into the infrared part of the spectrum. So this is a visible image of a star field which has been well studied in visible light. In the infrared, when we add the infrared from Spitzer, you see this group of reddish objects. We color code these objects so they look red in the infrared, even though you couldn't actually see the infrared light with your eye. We color code them because you wouldn't be impressed if I just showed you a bunch of ones and zeros. And this structure here is what's called a cluster of galaxies. It's a group of galaxies seen more than halfway across the universe, where there are plenty of galaxies in this picture, but they are closer and radiate. Their starlight comes to us in the visible part of the spectrum. When you move out to the infrared, you see more distant clusters of galaxies due to this phenomenon, which is called the cosmic redshift, which I'll be describing more about. But these objects are very far away. The light from them has taken billions of years to get here, and therefore we call them old. The cold refers to the fact that I mentioned earlier that astronomical objects radiate at a wavelength which is inversely proportional to their temperature. So in this picture of what's called the planetary nebula, which is a gel of dust and gas which has been thrown off by a bright star, the star is located more or less in the center of the picture on the left. When we look in the infrared, we see what is a cloud of dust surrounding the star. The dust absorbs the light from the star and radiates in the infrared, and that's that red spot that fills the cavity in the infrared image, and which can't be seen at all in the visible light. So this is the cold, and it illustrates an important fact that much of the infrared radiation we see comes from dust, which is heated by starlight to temperatures of a few hundred degrees, at which it re-radiates in the infrared part of the spectrum. And finally, we have the dirty, which alludes to the dust I already talked about, cosmic dust particles, which are very small, smaller than smoke grains, or than sand grains certainly, are ubiquitous in astronomical systems. And they do two things which are important. One is that they absorb visible light much more efficiently than they absorb infrared light, so that you can see through clouds of dust in the infrared that are opaque in the visible. And the other, as I mentioned earlier, is that frequently the dust absorbs the light from the stars, radiates in the infrared, and becomes a copious source of infrared radiation. So this is a visible wavelength image of a particular target in the sky. When I look in the infrared, it looks dramatically different, because you can see through this, the opaque region in the middle, around here, which is due to this cloud of dust, you can see into it and see young stars which are forming in this dense environment. And up here is a slightly older star, which formed maybe 2 million years ago, has gotten to the point where it can illuminate the surrounding material. And the red color there is due to emission from hydrocarbon molecules. The spectrum is shown here. So what we see here in the infrared is a progression of star formation from the upper left to the lower right. We know that these objects with wings sort of have outflows due to the process by which stars are forming. And it's comforting or encouraging or interesting to speculate that the stars first form up here in the upper left, And then the pressure of the starlight from those recently formed stars pushes on the material in this region and triggers the formation of additional generations of stars as the material is compressed and starts to collapse. I'll say a bit more about that in a second. Well, infrared astronomy began in earnest not long after World War II, driven by some of the technological developments of the war and by the fact that there were large telescopes on the ground which could be used for infrared work. But this should not be allowed to conceal the fact that infrared, a warm telescope on the ground, is not a good place to do infrared astronomy. And that's illustrated here. This is the Palomar Observatory, which I hope many of you visited, in San Diego County, operated by Caltech. For many years, the biggest telescope in the world. Still very important for research. During the day, the dome is closed because the astronomers are asleep, because they know you can't see the stars, if that's what they're trying to do, against the bright sky. You go back at night, as shown here, the dome is open and they're starting to peer out. And this all has to do with how bright the sky is. So if you go in the day and look up at the sky, it's bright and visible light because of the fact that the molecules in the atmosphere scatter sunlight. It's bright in the infrared because of the fact that the atmosphere and the telescope are warm in the infrared, and their radiation produces a bright infrared background. So if you go down one panel and come back at night, the sun's gone down, the sky is no longer bright, and you can see wonderful things like the Orion constellation in visible light. But infrared light, you're still blinded because of the fact that the atmosphere and the telescope are still warm. So what we've done with Spitzer and what's been done with JWST is to put a telescope in space and cool it with various technological approaches to the point where it's no longer warm enough to produce much infrared radiation. So a cold telescope in space, such as Spitzer or JW, allows us to work at night in the infrared. And that's the sort of a secret sauce, not such a secret, that's made Spitzer and JW so powerful. They're thousands of times more sensitive by virtue of being cold and in space than they would be on the ground. And the infrared image here is the complement to the Orion picture in the infrared. You can see the constellation sketch in there and these wonderful structures, clouds of dust and gas, not visible in the visible light image. Whoops, went too far. So let me give a quick, with that background, I could talk a bit about Spitzer. As I mentioned, it's NASA's great observatory for infrared exploration of the universe. It's an 85 centimeter cold telescope, covers wide wavelength range with imaging and spectroscopy. You can think of imaging as pictures, and spectroscopy is when you divide, which are diagnostic of the composition and physical conditions in the source you're observing. Very important for Spitzer is that we use large detector arrays, not individual pixels, but arrays which are similar in spirit to the cameras you all have in your cell phones, where everything is handled digitally. And our Spitzer arrays, although they're small by current standards, had tens of thousands of pixels. So if you have tens of thousands of pixels, each of which is 1,000 times more sensitive than it would be on a telescope on the ground, you get some idea of the kind of advances you get with a cold telescope in space. We've had over 10,000 refereed papers. And one of the novel things about Spitzer, this is the Earth, this is the sun. If you stood on the Earth, you'd see Spitzer moving away from you in orbit around the sun. So we launch Spitzer into orbit around the sun, because we wanted to get away from the heat of the Earth. And this allowed us to use a novel design for the cooling, which relied heavily on radiative cooling. Spitzer cools by radiating into the blackness of space, which is not so easy to do if you're in orbit around the Earth. We can talk more about how Spitzer works if you're interested. This is a good close-up view of the Spitzer, the solar panel, which collects the sunlight and remains oriented to the sun. The telescope and the instruments are in here. This black surface on this tube facilitates the loss of energy to space, the cooling, and then the spacecraft, which actually is a very expensive trucking service, sits down there. Along the way with Spitzer, we underwent many changes, and we went from this concept here to this one here between 1990 and 2003. They differ in that the telescope is launched warm here on the right and cools down into space, radiating into space. They have the same size telescope, the same lifetime, but vastly different in cost and launch mass. And this 2003 version, which is the one that's flying now, is a marvel of engineering. It's extraordinary how well it works. Okay, so I'm about to start talking about science. Are there any questions so far? Okay. So now let's talk about some of the Spitzer science. We'll start within the Milky Way. The Milky Way is the name we give to our galaxy. If you're in a dark sky at night and you can see the Milky Way, what you're really looking at is a plane of our galaxy. Our galaxy is a spiral galaxy like the ones you see in coffee table picture books. And if you're in the plane of that galaxy, when you look in the plane, you see what's shown here. If you look out of the plane, you can see deeper into space. This is a region a few degrees in size around the central core of our galaxy. The white spot here is a cluster of stars which sits at the center of the galaxy. This is a picture taken by Spitzer, and the red color is due to emission from the hydrocarbon molecules, which are also red in the earlier picture I showed of NGC 1533. And you can see a tremendous number of stars and clouds of dust, which are so opaque that they actually absorb the infrared radiation from these molecules and look opaque or dark here. When I started working in infrared astronomy 50 years ago, the cluster, the center of the galaxies had just been discovered by infrared observations from a small telescope at Mount Wilson, and they had one cut right across there. But now with the power of the detector arrays, you can get real images. And this is another image of a different part of the galaxy, the plane of the galaxy, just showing more of these dark clouds. And it's within dense, dark, dusty, and cold clouds that stars are forming. Even though our galaxy is probably around 12 billion years old, and the solar system is around 4.5 billion years old, new stars and new planets are forming within our galaxy, even as we speak. And I'll talk about Spitzer's studies of star and planet formation. The paradigm for star formation is illustrated here. If you just look at the pictures on the right, you have a dense condensation in one of these interstellar clouds of dust and gas, which becomes unstable to its own gravity. So it starts to collapse under its own weight. And as it collapses, it doesn't all collapse under the center because of the fact that it has some net rotation or angular momentum. And that material that's rotating has to go into a disk around the forming star. So here's the star that's forming. Here's the disk rotating around it. And here are what's called an envelope, which is additional material waiting to fall in. As this structure involves, it's dominated by the disk. And in our own solar system, even though we're no longer sitting in a dense disk, we do have a tenuous disk of dust associated with the planet. And you can see evidence of this process from our own solar system. All the planets in our own solar system go around the sun in the same direction, which is the direction in which the disk was rotating. And if you're ever fortunate enough to be up on a night where 4 or 5 planets can be seen at once, you see that they stretch across the sky in a line, more or less. The planets all lie in the same geometric plane, which is the plane of the disk out of which they form. So planets form in disks like this, and Spitzer has studied these planets, so-called exoplanets, around stars like the sun. Before that, we would look at these disks and study the material that's in them. So this is material out of which planets are forming. And depending on what direction you look in, if you look in the plane of the disk, through the disk, at the stars in the center, you might see what's called the spectrum that I mentioned earlier, great diagnostic power. It looks like this. And these bumps and wiggles can be identified as things like water ice, carbon dioxide ice, and the like. If you look directly in, so this is a disk which is differently oriented. In this one, our line of sight lies in the plane of the disk. Here the disk is a different disk with a different orientation, but schematically I've used only one disk here. You can see now emission features, again, from interesting molecules. Most of this is due to water and other molecules which are maybe important to the formation of life are included in these spectra. So our spectra of protoplanetary disks from Spitzer show what I call the stuff of life being incorporated into forming exoplanetary systems. Now, recent work shows that essentially all stars like the sun have one or more planets orbiting them. So if there's one takeaway from this talk, that's what you should take away. Planets can be hard to find. You can see here is the Earth, the sun. This is the Earth drawn to scale. This is not the scale, but this gives you an idea of how much brighter the sun is than the Earth. And so if you want to see the Earth by the sun, by some distant sun, it's a hard slog. So often planets are detected by virtue of their effect on the star they're orbiting. Here we see different ways of finding exoplanets. The two most popular ones are the radial velocity approach, where although the planet is orbiting the star, they're actually both orbiting around what's called the center of mass of the system. So the star has a velocity along our line of sight called the radial velocity, and as this planet orbits, pulls on the star as they orbit together, there's a small change in the orbital velocity of the star, which can be measured with precision instruments. So you're actually measuring velocities of the star as small as 1 meter per second, but that can actually be done quite reliably nowadays. And if that velocity is produced by a planet orbiting the star, it will repeat and have a behavior with time predicted by the laws of planetary motion. So you can infer both the presence of a planet and the mass of the planet from a radial velocity measurement. The other most promising technique or most popular technique, and this The radial velocity technique was the first one that was used. The transit photometry, the upper right, is the most popular one. Because you can look simultaneously at a bunch of stars with one of those detector arrays I told you about. And there are enough planets around those stars that some of them are oriented so that the planet moves in front of the star as we see it. And we detect that, what's called the transit, by the fact that the star dims temporarily. And this technique has been used by the Kepler mission to look at hundreds of thousands of stars simultaneously, only a fraction of the right orientation, but still thousands of stars have been identified by this transit photometry technique. I'll skip talking about the other two techniques unless there's a question later. And this is how the transit works. So here we see a picture of a star. The planet is going around the star, and we're in a position where we lie in the plane of that orbit, so we can see the planet transiting the star. So the planet goes in front of the star, it blocks the light from the star, and the star gets dimmer temporarily. The planet goes behind the star. As the planet moves behind the star, these planets have the property that they're tidally locked. So one face is always facing the star, and they have a hotter face, which is shown in red here. As more and more of that face comes to view, you see more and more infrared radiation from the combination of the, geez, I'm sorry, I should be a little more careful here. You see more and more infrared light from the combination of the star plus the planet until the planet goes behind the star. And if the planet is big enough and hot enough to have its own radiation, then when the planet goes behind the star, you see what's called an eclipse, because the light from the planet is no longer visible. So these transiting systems are our best means of discovering and one of the best means of studying exoplanet systems. Just to give you another view of it, here's a kind of a movie which shows the same process. Planet moves in front of the star, the light drops, the heated face of the planet becomes visible, more infrared radiation, the planet goes behind the star, the light drops again. And here you see the drop due to the eclipse, this brightening, which is called the phase curve, and then the drop due to the eclipse of the planet. You will always see the transit. You only see the eclipse when the planet is hot enough and big enough to have its own radiation in the infrared, but that often is the case. By studying in detail the shape of this curve, as more and more of this lit face becomes available, you can infer the temperature distribution there. And this is actually a map of the temperature distribution on the surface of a planet. Now, let me just remind you what we're looking at here. This is a planet orbiting a star perhaps 40 light years away. We have never seen the planet distinct separately, but I nevertheless have the audacity to tell you, not only is this a distribution of temperature on the surface of that planet, but it's actually not the hottest where you would expect it would be the hottest. You might expect that the planet would be hottest when the full illuminated face is looking at us, or when the hottest point on the planet is beneath in our line of sight. But in this planet, the hottest point is displaced. So what this tells us is that heat is being carried around the surface of the planet by winds in the atmosphere of the planet. So I can tell you if there is a planet, I can tell you something about the mass of the planet from radial velocity measurements. I can tell you the size of the planet, the density of the planet, the temperature of the planet, the temperature distribution of the planet, and what's going on in the planet's atmosphere, which is pretty remarkable since we've never actually seen the planet. And this is a tribute to the ingenuity of the people who have done these observations with Spitzer. I should also have said, if I can go back a couple, down here is where you can image planets and maybe study their composition in greater detail. Missions that start doing that are now being planned, and with luck, they will fly in our children's lifetime at least, and tell us something about whether some of these planets might be habitable. Now shows Spitzer's greatest hit, which is a star called TRAPPIST-1, which actually has, as you can count, 7 planets orbiting it. And these were discovered in 20 days of continuous monitoring by Spitzer. So if you look in the upper left, what's shown there is actually the brightness of the star as a function of time over 20 days, which we can do with Spitzer in its orbit. And all those downward excursions are due to transits of one or more of these planets. And this caused a great deal of excitement. It got us above the fold of the New York Times, and it got us a Google Doodle, which is the ultimate accolade. This was done in the infrared because the star is faint and red and is much better studied by Spitzer. In addition, Spitzer could have the uninterrupted viewing time, which was critical for this amazing discovery. This is a picture showing these 7 planets transiting the faint red star TRAPPIST-1. And the orbits are more or less to scale. And the cartoon there shows that water is vapor really close to the star because the star is so hot. Not that hot, but it's hot enough. The star is only slightly bigger than planet Jupiter. And all these planets that orbit it are about the size of the Earth. As you move out to more distant planets, you get liquid water. And so these planets might be appropriate for life as we understand it, based on water. And then in the outermost regions of the solar system, we have ice because those planets are colder. Looked at differently, this solar system, which I show as the upper system in this picture, would all fit within the orbit of Mercury, well within the orbit of Mercury, if they were in our solar system. And they have to be close because the star is pretty faint and couldn't heat them up very much if they were more distant. So what this shows is that anything that can happen will happen. People will say that this is extremely improbable, but that doesn't mean that it's impossible. No one knows how the system formed or what the implications are for the general study of exoplanet systems. I do want to point out on this plot, which shows some of the thousands of planets we now know about, this shows the period of the planet's orbit versus the mass of the planet. And if you see where the E is encircled, that's the Earth. Planet mass is 1 Earth mass. Period is about 360 days. But you notice that none of the planets in our solar system, which are shown by the encircled letters, lie in the part of this diagram where planets have been copiously discovered. So as much as work has been done on exoplanetary systems and as much technology has been developed, we still yet haven't gotten to the point where we can detect exact analogs to the planets in our solar system, which has given us an idea of how much excitement there is forthcoming. Although discovering planets with periods like Jupiter and Saturn, which are tens or dozens of years, might be difficult. Spitzer has also studied the solar system, and let me skip over this chart, but just point out that in one of these exoplanetary systems, if you look at the big panel on the left, there's another spectrum of the emission from dust in the exoplanet system. That's the green line. The orange line is the spectrum of dust in a comet in our own solar system, measured not by Spitzer, but by the European ISO mission. The fact that they're so similar tells us that the material in these two systems is very similar, and reminds us that we can learn a lot about exoplanet systems by studying our own solar system, which we can study in great detail. Conversely, we can learn a lot about our solar system by studying exoplanet systems, which we view from a favorable external vantage point. Now I'll talk a little about Spitzer's work on galaxies. This is a visible image on the left and a Spitzer image in the infrared on the right of a well-known galaxy, which is called either M51 or the Whirlpool Galaxy. And I'm sorry if this, you can see that the pictures are almost mirror images of each other. Regions which are dark in the visible wavelength image are bright here in the infrared because of the dust and molecules which reside there block the visible light but radiate in the infrared. You can see that this companion galaxy, which is distorted in the visible light, is pretty clean in the infrared. It's a ball of stars, so it's really the dust that's in and around this galaxy which is causing its tortured appearance. And you can see that there's a more compact nucleus here in the infrared, perhaps associated with a black hole, than is seen in the visible light, where there's more of a cluster of stars in the center. So when you look at the light from a galaxy, it radiates at many wavelengths. Here, this is a spectrum going from visible light to infrared to farther infrared. Here in visible light, if you look at a galaxy nearby, what you mainly see is light from stars. In the infrared, in the shorter bands, you see emission from the hydrocarbon molecules. Longer wavelengths, you see emission from dust heated by young stars. So the relative heights of the peaks in this picture tell us something about the star formation history of the galaxy. If a lot of stars formed a long time ago, there's no new action, there's no stars forming in dust clouds, there won't be that much infrared. Whereas if stars are forming copiously now, the dust may block the visible starlight, and the infrared radiation might dominate. Here are Spitzer pictures of a couple of fantastic galaxies. This one is called M101, the Sombrero. The blue cloud is actually a Hubble image of a cloud of stars which form the mass of the galaxy. And the red ring around it is infrared radiation that's seen by Spitzer. No one quite knows how the structure formed. It was probably through the merger of two galaxies, which occurs quite often, however. And this is another example. This is a exploding galaxy called M82. Again, is seen by Spitzer. Stars here in the plane of the galaxy, but I'm sorry. Stars here in the plane of the galaxy, and the red halo around it is again emissions from these hydrocarbon molecules that are being ejected from the plane of the galaxy by winds and supernovae and things like that, produced by recently formed stars. Pretty spectacular picture. Now let me talk about the cosmic redshift. which is what gets us into interesting territory. So because of the expansion of the universe, the wavelengths of light expand along with the universe. The expansion of the universe means that more distant objects are moving away more rapidly, and because of that, their light is shifted more and more into the infrared. The factor by which that occurs is called 1 plus z, where z is called the redshift. So if you look at this picture, the black spectrum is what a nearby galaxy would look like. The red spectrum is what that galaxy redshifted by a factor z equals 2, which you can see down in the lower right, means about 10 billion years ago. And that big peak in the black at the left, which is due to starlight, is now shifted towards the infrared, where it can be seen by Spitzer and where it's less readily seen in visible light. And that allows us to better understand what's going on here. Remember this picture, the visible light picture on the left, when you add the infrared, you see starlight from galaxies halfway across the universe or more, due to the redshift and the cosmic expansion. And that redshift makes the infrared invaluable for the study of the evolution and early life of the universe. Just jumping ahead, this is Spitzer's most distant galaxy, which is in a redshift of 11, which means that the universe was only 3% of its present age and 8% of its present size when the light that we now see left this very, very distant galaxy. It's been shifted in wavelength by a factor of 12 because of the expansion of the universe over the time that it took it to get here. And early on in the Spitzer mission, it was clear that these galaxies that Spitzer and Hubble are seeing and studying at high redshift pose a cosmic conundrum because they're much more massive and mature than were expected by existing theories before these measurements were made. And so these results challenge theories of structure, formation in the early universe, and this study of distant galaxies in the early universe will be a prime area of study for James Webb Space Telescope because of its greater power than Spitzer or Hubble. So to learn more about Spitzer, I recommend a book, which I and my colleague Peter Eisenhart, some of you might know him if you're members of Neighborhood Church. We wrote this book together. It's been published by Princeton University Press and is available on Amazon. If you get a copy, I'll be glad to sign it for you. Okay, so now it's time to talk a little bit about James Webb. Okay, this is a picture of the James Webb Telescope. The Webb Telescope folded up like an origami bird and was wedged or crammed into a launch cone, a nose cone of a launch vehicle. And this is a remarkable picture. I think this is the Red Sea here, of James Webb as it was leaving its rocket to go into its orbit. And it hasn't yet started to unfold. So at this point, it's a huge cylinder. James Webb was judged in the year 2000 to be the highest priority for U.S. space astronomy. It's a 6.5 meter telescope made of segments, but it's much, much bigger than Spitzer, which is only 85 centimeters, less than a meter, and then Hubble, which is about 2.2 meters. It has a complex structure which unfolded flawlessly on orbit. It was quite expensive and took a long time to build, but they now expect at least a 10-year mission, a huge gain over previous missions, The early data released since June were very exciting and show tremendous promise. And unlike the other great observatories, James Webb was named for an early NASA administrator, James Webb, who was actually influential in establishing NASA's science program. Spitzer was named for Lyman Spitzer, who was a visionary astrophysicist who in the 1940s predicted the eventual use of space for astronomy in the optical and other parts of the spectrum. Here's some pictures of James Webb. Again, the people shown for scale emphasize the size. And if you compare the picture on the left with the picture on the upper right, you can see that the rightmost set of three mirrors in the picture on the left has been folded back behind the rest of the mirror structure in the picture on the right. This is all prior to getting it packed up into the nose cone, and that structure that hangs in front of the mirror panels, you can see it unfolded in the engineering drawing to the right. That's what carries the secondary mirror of the telescope. So in that picture, the telescope is up at the top. The instruments are back here. The light hits the primary mirror, the secondary mirror comes back to the instruments. This is a sun shield, the size of a tennis court, which protects the cold telescope from the heat of the sun. And this is a spacecraft, which again is an expensive tracking system. And I should have mentioned that Spitzer carried some stored cryogen, liquid helium, which kept us cold for the first 5.5 to 6 years. And then the rest of the time we relied on the coldness of space to keep us cold and the clever design. In the case of James Webb, which doesn't get as cold, there's no stored cryogens at all. They're going to rely entirely, or they're relying entirely on this coldness of space to cool the telescope off. That's why the sunlight is blocked out. And then there's a mechanical device with a long lifetime, which brings some of the detectors down to operating temperature. But there's not a stored cryogen of limited lifetime. Another interesting thing about James Webb is the orbit. Here again, you see the sun and the Earth, and James Webb is out here near what's called L2, which is a point which is stable in the Earth-Sun rotating system. So as the Earth rotates around the sun, the L2 point rotates as well to continue to be on the same line which connects the sun and the Earth. And the James Webb Space Telescope, being in orbit around the L2 point, is readily accessible for communications with the Earth. This orbit has a lot of the advantages that the Spitzer solar orbit had, with the additional advantage of being closer, which improves communications. So, Bob, how are we doing for time?
Well, I think we can go more.
Okay, I'll finish up with some James Webb data. So this is one of the first images released from James Webb. It's what's called the deep image, or looking at the one piece of the sky for a long time. The circle in red encircles a cluster of galaxies, a group of galaxies, which is a large concentration of matter. And the arcs that you can see to the left of it are actually more distant galaxies, which are lensed by the mass of this cluster of galaxies and stretched in a characteristic way, which you can see. So this prediction of lensing by mass concentrations was made by Einstein, or results from Einstein's work, has been verified in the past, and it's dramatically illustrated in this picture from the Webb telescope. And deep surveys like this, which look very far back in space and time, will be key elements of the James Webb Science Program. We all know how powerful the Hubble Space Telescope was. This is a Hubble image of the same field, which is spectacular in itself, but clearly missing a lot of the detail and excitement that you can see in the James Webb image. Perhaps the most interesting images in this field from James Webb are, this is a subset of the field, obscure little galaxies like the one shown up here, which are very old. And when we look at them, we're looking very back to the dawn of time. The universe is about 13.8 billion years old. And what's exciting about these objects in James Webb is that James Webb can actually get spectra, as sort of shown below, which can determine the composition of the gas in these galaxies. And remember that when the universe was formed, only hydrogen and helium were formed. All the other elements in the periodic table, excepting for some of the lithium, beryllium, and boron, were formed in stars and ejected into the interstellar medium as the stars lose mass during their evolution. So by studying the composition of the gas in galaxies like this, we can actually map out the growth of the chemical elements and also the cosmic dust particles with cosmic time, which is extremely interesting and important. James Webb can determine the composition of exoplanet atmospheres, and here's evidence for carbon dioxide in the atmosphere of an exoplanet. The white points are the data, the blue is the model calculation, which fits the data very well. This is a comment James Webb builds upon and extends the exploration of the universe from space, exemplified by Hubble and Spitzer, and pushed forward by scientists, engineers, and space agencies from around the world. Space exploration is a truly international affair, and there are powerful infrared facilities that have been launched both by no longer operating, but have been launched in the past both by the European Space Agency and by the Japanese Space Agency. And this is one more picture from James Webb, hot off the press. This is a picture of the Neptune system, which shows several of the moons of Neptune. The planet Neptune, this is taken at a wavelength where the Neptune absorbs most of the incident radiation, and even the rings of Neptune can all be seen in this wonderful picture from James Webb. And this is yet another remarkable picture, which is a series of shells. The stars there are a pair of stars at the center. They each have winds of material which is escaping from them. They're losing mass, and when these winds collide, the orbit of the stars around one another is eccentric. So every 8 or 9 years, they get really close together. And when the winds collide, the material in the winds is compressed and forms dust. And that appears in successive occurrences. The dust expands outward from the star. And you look at it now, you can see 10 or 12 of these dust rings going back well over 100 years, all of which are heated by the central star and radiated in the infrared. That's an amazing picture. And as I point out, we are all fortunate to live in a society which has the resources and the will to continue to support the universe and man's place in it. And finally, in our book, we have lots of great epigrams, and this is one of the best from T.S. Eliot. what we call the beginning is often the end. We shall not cease from exploring, and the end of all our exploring will be to arrive where we started and know the place for the first time. And finally, I'm off on my next adventure, which is a much, much smaller mission called Spherex, launching in 2025 and obtaining spectra across the sky in the infrared. So I hope this has given you some idea of the excitement and importance of infrared astronomy. And of course, I'll be happy to answer questions. If you want to moderate, Bob, that's fine, or people can just speak up.
Well, I think, there's a thing where you can raise your hand in the Zoom, raise your hand electronically. And maybe what we should do is turn off the screen sharing for the questions. You can always turn it back on.
Okay. How's that?
Well, I think that's pretty good. Do we have any questions? Anybody that has some comment or a question they wish to ask?
I think I, for one, feel too ignorant to ask a question, but it was fascinating to listen to you.
Well, don't describe yourself as ignorant. There are no dumb questions.
Okay.
They're only bashful people. But thank you.
Michael, the question is, having seen the spectra of these distant planets, what's the goal of the science?
Of the study of exoplanets?
Of studying the spectra with the infrared light, with the infrared telescope.
Yeah. Well, the goal is, and it's not done only in the infrared, to determine whether planets around stars like the sun have conditions which are conducive or consistent with the formation of life. And you do that by measuring the chemical composition of the atmosphere by looking at the molecules it contains, and by looking for anomalies which are best explained by life on those planets. Life, we have a lot more oxygen and ozone in the atmosphere of our planet than we would have if there weren't people here, or life rather. So life can leave chemical markers that we might be able to discern with remote observations from systems beyond even JWST.
What do you think of the theory that I've only recently heard that the universe had no beginning?
Well, there's little question. You can always, all the data we have are consistent with the idea that the universe that we know and live in formed in a Big Bang 13.8 billion years ago. Now, there may be other universes that we don't know about, which predated our universe. And that certainly, there are certainly theories of multiverses, which I only know the word, I don't know anything about it. And I suppose in a multiverse, you might get down to the idea that the universe is infinite. But the universe that we know and love by all scientific investigations started in a Big Bang about 13.8 billion years ago. And that Big Bang created both matter and space and time. So you don't think of the universe expanding into anything. You think of the universe carrying itself along as it expands.
I have sort of a negative view of the idea of our populating another planet, because when I look at what we've done to this one, I'm not sure we would be welcome Do we have 30 seconds for me to read my most recent poem because it applies directly to what we're talking about?
It's fine with me.
May I share? It's
Sure.
called Alien Observation. If you were an alien here from outer space to make some observations about the human race, you would look around you to take time to absorb, send some detailed chronicles back to your home orb. Into your shiny spaceship, you would quickly flee back to your normality, a place where you are free. You tell the other aliens of our pain and our disgrace, of how earthlings have fallen on our collective face. Your spaceships will be parked in a neat and tidy row with few pilots to fly them. Now they're in the know. You'll look around your galaxy, realize you do things right, and hope some ugly humans don't move in tonight.
Bravo.
Good.
Sorry, I just had to share that. That was
Oh,
new
that was
last
good.
week. And I've become a bit of a misanthrope, I have to say, about the human race.
Well, it's easy to do that these days. And I think the idea of us inhabiting another planet, even Mars, which is the closest in any mass way, is pretty much of a pipe dream, certainly now, and probably will be for many decades to come.
Michael, that was fascinating. I think we should give Michael a round of applause too.
Yeah,
Thank
it
you
was
very
really
much.
Thank
interesting.
you. I'm going to stop the recording, but it doesn't mean you can still ask questions.
Okay, done.